4.5 billion years ago, when Earth was still a molten hellscape being bombarded by asteroids, a world not so different from ours was taking shape 48 million miles away. Mars, the red planet, has captivated humanity for millennia, appearing as a wandering red star in our night sky. But what we've discovered about this alien world in recent decades has shattered every assumption we had about planetary evolution, the possibility of life beyond Earth, and our own cosmic destiny. And here's something I'm genuinely curious about. If you could ask the first human to set foot on Mars one question about what they see, what would it be? Let me know in the comments down below. I will pin the most creative answer. Now let's begin this incredible journey. Mars is a world of extremes that challenges everything we thought we knew about planetary science. With a diameter of 6,792 kilometers, roughly half the size of Earth, this rusty world spins on its axis every 24 hours and 37 minutes, giving it days remarkably similar to our own. But that's where the similarities end, and the alien nature of Mars begins to reveal itself. The Martian year stretches for 687 Earth days as it follows an elliptical orbit that carries it between 207 million and 249 million kilometers from the Sun. This eccentric path creates dramatic seasonal variations that make Earth's climate changes seem gentle by comparison. When Mars reaches its closest approach to the Sun, called perihelion, the southern hemisphere experiences a brief but intense summer with temperatures that can actually reach a pleasant 20 degrees Celsius in some regions. But don't pack your beach gear just yet. The average temperature on Mars hovers around -63 degrees Celsius, cold enough to freeze carbon dioxide out of the atmosphere and create polar ice caps that grow and shrink with the seasons. During the harsh Martian winter, temperatures can plummet to -125 degrees Celsius at the poles, colder than the coldest temperature ever recorded on Earth. The atmosphere of Mars tells a story of planetary tragedy that scientists are still working to understand. Today, the Martian atmosphere is incredibly thin, less than 1% the density of Earth's atmosphere, composed primarily of carbon dioxide with traces of nitrogen and argon. The atmospheric pressure at the surface is so low that liquid water cannot exist in most regions, immediately boiling away into the thin air. This wasn't always the case. Evidence from NASA's MAVEN mission, which has been studying the Martian atmosphere since 2014, reveals that Mars once possessed a much thicker atmosphere capable of supporting liquid water on its surface. The spacecraft has detected the ongoing escape of atmospheric gases into space, stripped away by solar wind because Mars lacks the strong magnetic field that protects Earth's atmosphere. The loss of Mars's magnetic field represents one of the most significant events in planetary history. Unlike Earth, which maintains a powerful magnetic field generated by its molten iron core, Mars lost its global magnetic field approximately 4 billion years ago. The Mars Global Surveyor mission discovered remnant magnetic fields in the planet's ancient crust, particularly in the southern highlands, providing evidence that Mars once had a magnetic field similar to Earth's. Without this protective magnetic shield, the solar wind, a stream of charged particles flowing from the Sun, began systematically stripping away the Martian atmosphere. Over billions of years, this process transformed Mars from a potentially habitable world with flowing rivers and standing bodies of water into the cold, dry desert we see today. The surface of Mars reveals a geological history that spans billions of years and includes some of the most extreme features in the solar system. Olympus Mons, the largest volcano in the solar system, rises 21 kilometers above the surrounding plains, nearly 2.5 times taller than Mount Everest. This massive shield volcano covers an area roughly the size of France and represents volcanic activity that continued for billions of years. The Tharsis volcanic region, where Olympus Mons is located, contains 4 massive volcanoes that dwarf anything on Earth. These geological giants formed because Mars lacks plate tectonics, the process that moves continents around on Earth's surface. Without moving plates to carry volcanic hotspots to new locations, Martian volcanoes could grow continuously in the same spot for billions of years, reaching truly enormous proportions. Valles Marineris, the Grand Canyon of Mars, stretches over 4,000 kilometers across the planet's surface, roughly the distance from New York to Los Angeles. This massive canyon system reaches depths of up to 7 kilometers and widths of 600 kilometers in some places. Unlike the Grand Canyon on Earth, which was carved by flowing water, Valles Marineris appears to have formed through tectonic processes related to the formation of the Tharsis volcanic region. The dichotomy between Mars's northern and southern hemispheres represents one of the planet's most puzzling features. The northern hemisphere consists primarily of smooth, low-lying plains that may once have been covered by an ocean, while the southern hemisphere is dominated by heavily cratered highlands that preserve the scars of the solar system's violent early history. This dramatic difference in elevation and surface features has led scientists to propose several theories for its origin. Some suggest that a massive impact early in Mars's history created the northern lowlands, while others propose that internal geological processes were responsible. The Mars Reconnaissance Orbiter and other missions continue to study this global dichotomy, searching for clues about the planet's early evolution. The polar regions of Mars contain vast ice caps composed of both water ice and frozen carbon dioxide. The northern polar cap is primarily water ice and remains frozen year-round, while the southern polar cap contains both water ice and seasonal carbon dioxide ice that sublimates during the Martian summer. These polar ice caps represent the largest known reservoirs of water on Mars today. The Phoenix lander, which touched down near the North Pole in 2008, confirmed the presence of water ice just beneath the surface and detected snow falling from Martian clouds. The Mars Polar Lander mission, though it failed to successfully land in 1999, was designed to study these polar regions and search for evidence of climate change on Mars. If you're finding these Martian discoveries as mind-blowing as I am, take a second to hit that subscribe button and give this video a thumbs up. We're uncovering some of the most profound mysteries in our solar system together, and your support helps me continue bringing these incredible scientific breakthroughs to light. Trust me, the discoveries we're about to explore next will completely change how you think about the possibility of life beyond Earth. Recent discoveries by the Mars Reconnaissance Orbiter have revealed that the polar ice caps contain detailed records of Martian climate history, similar to ice cores on Earth. Layers in the ice caps correspond to different periods in Mars's past, potentially preserving information about atmospheric conditions, dust storms, and volcanic activity over millions of years. The search for water on Mars has been one of the driving forces behind planetary exploration for decades. While liquid water cannot exist on most of the Martian surface today, due to the low atmospheric pressure and cold temperatures, overwhelming evidence suggests that water once flowed freely across the planet. Orbital images reveal ancient river valleys, delta formations, and what appear to be dried lake beds scattered across the Martian surface. These features, carved billions of years ago when Mars had a thicker atmosphere and warmer climate, tell the story of a world that was once much more Earth-like than the frozen desert we see today. The Mars Global Surveyor mission, which operated from 1997 to 2006, provided the first detailed maps of these ancient water features. The spacecraft's high-resolution cameras revealed intricate networks of valleys that could only have been carved by flowing water, along with layered rock formations that suggest the presence of ancient lakes and seas. The European Space Agency's Mars Express mission, launched in 2003, has provided even more compelling evidence for ancient water activity. The spacecraft's radar instrument Marsis has detected subsurface water ice deposits and possible liquid water reservoirs beneath the Martian surface. These discoveries suggest that significant amounts of water may still exist on Mars, locked away in underground aquifers or frozen in the soil. One of the most exciting recent discoveries came from the Mars Reconnaissance Orbiter's detection of recurring slope lineae, dark streaks that appear and disappear seasonally on steep Martian slopes. Initially thought to be evidence of flowing liquid water, these features have sparked intense debate among scientists about the possibility of liquid water activity on present-day Mars. The Curiosity rover, which landed in Gale Crater in 2012, has revolutionized our understanding of Mars's watery past. The rover's analysis of rocks and sediments has revealed that Gale Crater once contained a lake that persisted for millions of years. The chemical composition of these ancient lake sediments suggests that the water was relatively fresh and could have supported microbial life. Curiosity's discovery of organic molecules in Martian rocks represents one of the most significant findings in the search for life beyond Earth. These carbon-based compounds detected in rocks that are over 3 billion years old could be the remnants of ancient life or the building blocks from which life could have emerged. While the presence of organic molecules doesn't prove that life existed on Mars, it demonstrates that the planet once had the chemical ingredients necessary for life as we know it. The Perseverance rover, which landed in Jezero Crater in 2021, is specifically designed to search for signs of ancient microbial life. Jezero Crater was chosen as the landing site because orbital observations revealed clear evidence of an ancient river delta, a location where sediments and potentially fossilized microorganisms could have been preserved for billions of years. Perseverance carries the most sophisticated suite of scientific instruments ever sent to Mars, including ground-penetrating radar, spectrometers capable of detecting organic molecules, and a sample collection system that will gather rock and soil samples for eventual return to Earth. The rover's MOXIE experiment has already demonstrated the ability to produce oxygen from the Martian atmosphere, a crucial technology for future human missions. Speaking of the challenges of reaching Mars, the journey to the Red Planet represents one of the most complex undertakings in human history. If you're curious about why getting to Mars is so incredibly difficult and the engineering marvels required to make it happen, you should check out my video, This is Why We Can't Reach Mars. It explores the mind-bending physics, timing constraints, and technological hurdles that make Mars missions some of the most challenging endeavors ever attempted by humanity. The link is in the description and on the card above. The Ingenuity helicopter, which accompanied Perseverance to Mars, achieved the first powered flight on another planet in April 2021. This small rotorcraft, weighing just 1.8 kilograms, has far exceeded its planned mission duration and demonstrated that aerial exploration of Mars is not only possible, but incredibly valuable for future missions. Flying on Mars presents unique challenges due to the thin atmosphere, which has a density less than 1% of Earth's atmosphere at sea level. To generate enough lift, Ingenuity's rotors must spin at over 2,400 revolutions per minute, much faster than helicopters on Earth. The success of Ingenuity has paved the way for future aerial vehicles that could explore regions of Mars inaccessible to rovers. The geology of Mars reveals a complex history of volcanic activity, impact cratering, and erosion that spans the planet's entire 4.5 billion year existence. The Martian surface is divided into three major geological periods: the Noachian, Hesperian, and Amazonian epochs, each characterized by different environmental conditions and geological processes. The Noachian period, lasting from Mars's formation until about 3.7 billion years ago, was characterized by heavy bombardment from asteroids and comets, extensive volcanic activity, and the presence of liquid water on the surface. This was the era when Mars most closely resembled early Earth, with a thicker atmosphere and warmer climate that could have supported life. During the Hesperian period from 3.7 to 3 billion years ago, Mars began its transition to the cold, dry world we see today. Volcanic activity continued, but the atmosphere was already thinning, and liquid water became increasingly rare on the surface. The massive outflow channels that carved some of Mars's most dramatic landscape features formed during this period. The Amazonian period, from 3 billion years ago to the present, represents the current era of Martian geology. This period has been characterized by limited geological activity a thin atmosphere, and surface conditions hostile to liquid water. However, recent discoveries suggest that even during this period, Mars has experienced episodic volcanic activity and possible subsurface water activity. The mineralogy of Mars provides crucial insights into the planet's past environmental conditions. The Mars exploration rovers Spirit and Opportunity, which landed in 2004, discovered evidence of past water activity through the identification of minerals that form only in the presence of liquid water. Hematite, jarosite, and other hydrated minerals found by these rovers indicate that Mars once had environments with neutral to acidic water that could have been habitable. The Mars Science Laboratory mission, which delivered the Curiosity rover to Gale Crater, has identified clay minerals that form under relatively mild, neutral pH conditions, exactly the type of environment that could have supported life. These discoveries have fundamentally changed our understanding of Mars's habitability potential and have guided the selection of landing sites for future missions. Seasonal changes on Mars create some of the most dynamic and visually spectacular phenomena in the solar system. The planet's axial tilt of 25 degrees, similar to Earth's 23.5 degrees, creates distinct seasons. But the elliptical orbit and thin atmosphere make these seasonal changes far more extreme than anything experienced on Earth. During the Southern Hemisphere's summer, when Mars is closest to the Sun, massive dust storms can engulf the entire planet for months at a time. These global dust storms, which occur roughly every few years, can completely obscure the surface and dramatically affect the planet's temperature and atmospheric circulation patterns. The 2018 global dust storm that lasted for several months provided scientists with an unprecedented opportunity to study these phenomena. The storm was so intense that it effectively ended the mission of the Opportunity rover, which had been operating on Mars for nearly 15 years. The dust blocked sunlight from reaching the rover's solar panels, eventually leading to the loss of communication with the spacecraft. Martian dust devils, towering columns of rotating air and dust, are common features on the planet's surface. These phenomena can reach heights of several kilometers and have been observed by both orbital spacecraft and surface rovers. Unlike dust devils on Earth, Martian dust devils can be much larger and more persistent due to the planet's thin atmosphere and extreme temperature variations. The moons of Mars, Phobos and Deimos, are among the smallest moons in the solar system and likely represent captured asteroids rather than objects that formed alongside Mars. Phobos, the larger of the two moons, orbits just 6,000 kilometers above the Martian surface, closer than any other moon to its parent planet in the solar system. Phobos is gradually spiraling inward toward Mars due to tidal forces and will either crash into the planet or be torn apart by gravitational forces within the next 50 million years. This doomed moon provides a unique natural laboratory for studying tidal interactions and the evolution of small bodies in the solar system. The origin of Phobos and Deimos remains a subject of scientific debate. While their irregular shapes and composition suggest they are captured asteroids, their nearly circular orbits around Mars's equator are difficult to explain through simple capture scenarios. Some scientists propose that these moons formed from debris created by a massive impact on Mars early in the planet's history. Future missions to Mars will continue to build on the incredible discoveries of the past few decades. The European Space Agency's ExoMars mission, delayed but still planned for the coming years, will include a rover specifically designed to drill deep beneath the Martian surface in search of signs of life. This mission will complement NASA's ongoing exploration efforts and provide new insights into Mars's potential for past or present life. The Mars Sample Return mission, a joint effort between NASA and the European Space Agency, represents the next major milestone in Mars exploration. This ambitious mission will collect the samples gathered by the Perseverance rover and return them to Earth for detailed analysis in terrestrial laboratories. The ability to study Martian rocks and soil with the full range of analytical techniques available on Earth could finally answer the question of whether life ever existed on Mars. The Mars Sample Return mission represents one of the most complex robotic missions ever attempted, requiring multiple spacecraft working in perfect coordination across millions of kilometers of space. The mission involves launching a fetch rover to collect Perseverance's samples, transferring them to a Mars ascent vehicle that will launch the samples into Martian orbit, and finally capturing them with an Earth return orbiter for the journey back to our planet. The technical challenges of this mission are staggering. The Mars ascent vehicle will become the first rocket ever launched from the surface of another planet, while the orbital rendezvous and sample capture must be executed with precision that makes docking at the International Space Station look simple by comparison. If successful, these Martian samples will arrive on Earth sometime in the early 2030s, potentially carrying the first definitive evidence of life beyond our planet. The search for life on Mars has evolved dramatically as our understanding of the planet has deepened. Early missions focused on detecting obvious signs of life, green vegetation or large organisms that might be visible from orbit. Today's approach is far more sophisticated, recognizing that if life exists or existed on Mars, it was most likely microbial and may have left only subtle chemical signatures in the rock record. The Viking missions of 1976 conducted the first direct search for life on Mars, carrying biological experiments designed to detect metabolic activity in Martian soil. The results were tantalizingly ambiguous. Some experiments showed positive results that could indicate biological activity, while others suggested purely chemical explanations. Decades later, scientists continue to debate the Viking results, with some arguing that the experiments may have actually detected microbial life. Modern astrobiology approaches the search for life on Mars through multiple complementary strategies. Rather than looking for life directly, scientists search for biosignatures, chemical or physical evidence that life processes have occurred. These might include specific organic molecules, isotopic ratios that indicate biological activity, or mineral formations that require the presence of living organisms. The discovery of methane in the Martian atmosphere has created one of the most intriguing mysteries in planetary science. Methane is a simple molecule that can be produced by both geological and biological processes, but it's also destroyed relatively quickly by ultraviolet radiation in Mars's thin atmosphere. The presence of methane suggests that something is actively producing it on present-day Mars. The Curiosity rover has detected seasonal variations in atmospheric methane concentrations, with levels rising during the Martian summer and falling during winter. This seasonal pattern suggests that the methane source is somehow connected to temperature changes, possibly involving the release of trapped gases from subsurface reservoirs or seasonal biological activity. The European Space Agency's Trace Gas Orbiter, part of the ExoMars program, was specifically designed to study trace gases in the Martian atmosphere, including methane. Surprisingly, the spacecraft has detected much lower methane concentrations than previous missions, creating a puzzle about the temporal and spatial variability of methane on Mars. This discrepancy highlights how much we still don't understand about atmospheric processes on the red planet. Subsurface environments on Mars may represent the most promising locations for finding present-day life. While the surface is hostile to life as we know it, conditions several meters below ground could be much more hospitable. The subsurface is protected from harmful radiation, experiences more stable temperatures, and may contain liquid water in the form of brines, salty solutions that remain liquid at temperatures well below the freezing point of pure water. The Phoenix lander's discovery of perchlorate salts in Martian soil initially seemed to make the planet even more hostile to life, as these chemicals are toxic to most Earth organisms. However, some extremophil bacteria on Earth can actually use perchlorates as an energy source, suggesting that similar organisms might be able to survive in Martian soil. Recent research has shown that perchlorate brines can remain liquid at Martian surface temperatures and pressures, potentially creating microenvironments where life could exist. These discoveries have shifted the focus of astrobiology from searching for past life to considering the possibility that Mars might still harbor living organisms in specialized ecological niches. The concept of a Martian biosphere has evolved from science fiction to serious scientific consideration. If life exists on Mars today, it would likely be confined to subsurface environments where conditions are more stable and protected from the harsh surface environment. This hypothetical biosphere might be completely independent of surface conditions, deriving energy from chemical reactions involving rocks and minerals. Deep subsurface life on Earth provides compelling analogies for potential Martian organisms. Scientists have discovered thriving microbial communities kilometers beneath Earth's surface, living in environments with no sunlight, extreme temperatures, and high pressure. These organisms derive energy from chemical reactions involving rocks and water, demonstrating that life can exist in conditions previously thought to be uninhabitable. The study of extremophiles, organisms that thrive in extreme environments, has revolutionized our understanding of life's limits and expanded the range of conditions where we might expect to find life on Mars. From bacteria living in highly acidic hot springs to organisms thriving in the intense radiation environment around nuclear reactors, life on Earth has proven remarkably adaptable to hostile conditions. Martian meteorites found on Earth have provided unique insights into the red planet's composition and history. These rocks, blasted off Mars by asteroid impacts and eventually falling to Earth, represent the only samples of Mars that scientists can study in terrestrial laboratories with the full range of analytical techniques available. The most famous Martian meteorite, ALH 84001, sparked intense controversy in 1996 when NASA scientists announced they had found possible evidence of ancient microbial life within the rock. The evidence included microscopic structures that resembled fossilized bacteria, organic molecules, and mineral formations that could indicate biological activity. The claims about ALH 84001 remain highly controversial, with most scientists now favoring non-biological explanations for the observed features. However, the meteorite studies have provided valuable insights into Mars's early environment and have refined the techniques used to search for biosignatures in Martian rocks. Other Martian meteorites have revealed important information about the planet's geological history and the presence of water in Mars's past. Some meteorites contain minerals that formed in the presence of liquid water, while others preserve evidence of the planet's early magnetic field and atmospheric conditions. The climate history of Mars represents one of the most dramatic planetary transformations in the solar system. Evidence suggests that early Mars had a much thicker atmosphere, possibly containing significant amounts of water vapor and carbon dioxide that could have created a greenhouse effect warm enough to support liquid water on the surface. The transition from this early, potentially habitable Mars to the cold, dry planet we see today occurred over hundreds of millions to billions of years. Multiple factors contributed to this transformation, including the loss of the planet's magnetic field, atmospheric escape to space, and changes in solar luminosity over geological time. Climate models of early Mars face significant challenges in explaining how the planet could have been warm enough to support liquid water. The young sun was about 30% dimmer than it is today, creating what scientists call the faint young sun paradox. Despite this reduced solar heating, geological evidence clearly indicates that liquid water was present on early Mars. Proposed solutions to this paradox include a much thicker carbon dioxide atmosphere that could have created a strong greenhouse effect, the presence of other greenhouse gases like methane or hydrogen, or episodic warming events caused by volcanic activity or asteroid impacts. Each of these scenarios has different implications for Mars's habitability and the potential for life to have emerged and evolved on the planet. The role of impacts in shaping Mars's evolution cannot be overstated. The planet's surface preserves a detailed record of the solar system's violent early history, when asteroids and comets bombarded the inner planets in an event known as the Late Heavy Bombardment. This period, which occurred roughly 4 billion years ago, may have delivered significant amounts of water and organic molecules to Mars, while simultaneously creating conditions that could have been either beneficial or harmful to emerging life. Large impact basins like Hellas Planitia and Argyre Planitia represent some of the largest impact structures in the solar system. These massive craters formed by asteroid impacts early in Mars's history created deep basins that may have served as reservoirs for ancient lakes or seas. The heat generated by these impacts could have created hydrothermal systems that might have provided energy sources for early life. The study of impact processes on Mars has also revealed important information about the planet's interior structure and composition. The way that impact craters form and evolve depends on factors like gravity, atmospheric density, and subsurface properties. By studying Martian craters and comparing them to similar features on other planets, scientists can infer details about Mars's internal structure and geological history. Volcanic activity on Mars has played a crucial role in shaping the planet's surface and atmosphere throughout its history. The massive shield volcanoes in the Tharsis region represent some of the largest volcanic constructs in the solar system, built up over billions of years of eruptions. These volcanoes may have been active much more recently than previously thought, with some evidence suggesting eruptions within the past few million years. The longevity of Martian volcanic activity has important implications for the planet's habitability. Volcanic processes can release water vapor and other gases into the atmosphere, potentially creating temporary periods of more hospitable conditions. Hydrothermal systems associated with volcanic activity could also provide energy sources and chemical environments suitable for life. Recent analysis of Martian meteorites has revealed evidence for relatively recent volcanic activity, challenging previous assumptions about when Mars became geologically inactive. Some meteorites appear to have crystallized from magma just a few 100 million years ago, recent in geological terms and suggesting that Mars may still be volcanically active today. The discovery of possible recent volcanic activity on Mars has profound implications for the planet's potential habitability. Active volcanism could provide heat sources that maintain subsurface liquid water, create chemical environments suitable for life, and release gases that could temporarily thicken the atmosphere. The Mars Express Orbiter has detected what appear to be very young lava flows in several regions, suggesting that Mars may not be the geologically dead world scientists once believed. Hydrothermal systems on Mars represent some of the most promising environments for past or present life. On Earth, hydrothermal vents on the ocean floor support thriving ecosystems that derive energy from chemical reactions rather than sunlight. Similar systems may have existed on Mars when the planet had liquid water on its surface, and they might still exist in subsurface environments today. The Spirit rover made a remarkable discovery in Gusev crater when it found evidence of ancient hydrothermal activity in the form of silica deposits that could only have formed in hot water environments. These deposits, similar to those found around geysers and hot springs on Earth, suggest that Mars once had active hydrothermal systems that could have provided ideal conditions for life to emerge and thrive. Opportunity's exploration of Meridiani Planum revealed extensive evidence of past water activity in the form of sulfate minerals and sedimentary rock layers that clearly formed in aqueous environments. The rover's 14-year mission provided unprecedented insights into Mars's watery past and demonstrated that liquid water persisted on the planet's surface for extended periods. The discovery of recurring slope lineae, dark streaks that appear seasonally on steep Martian slopes, initially generated excitement about the possibility of present-day liquid water activity. However, subsequent analysis has suggested that these features might be caused by flowing sand rather than water, highlighting the challenges of interpreting remote observations of planetary surfaces. Despite this setback, other evidence for present-day water activity continues to accumulate. The Mars Reconnaissance Orbiter has detected what appear to be seasonal changes in crater walls that could indicate the flow of briny water, while radar observations have identified possible subsurface liquid water reservoirs beneath the planet's polar ice caps. The search for subsurface water on Mars has been revolutionized by ground-penetrating radar instruments on various spacecraft. The Marsis radar on Mars Express and the Sharad radar on the Mars Reconnaissance Orbiter have mapped subsurface ice deposits across much of the planet, revealing that Mars contains vast amounts of frozen water just beneath its surface. These subsurface ice deposits represent a crucial resource for future human missions to Mars. Water can be split into hydrogen and oxygen for rocket fuel, used for drinking and agriculture, and provide radiation shielding for habitats. The widespread distribution of subsurface ice means that future Mars explorers will have access to water resources in many different regions of the planet. The seasonal behavior of Mars's polar ice caps provides insights into the planet's atmospheric dynamics and climate history. Each Martian winter, carbon dioxide freezes out of the atmosphere at the poles, creating seasonal ice caps that can extend to latitudes equivalent to those of Canada on Earth. During spring and summer, this carbon dioxide ice sublimates back into the atmosphere, creating dramatic seasonal changes in atmospheric pressure. The Mars Reconnaissance Orbiter has captured spectacular images of these seasonal changes, including geysers of carbon dioxide gas erupting through the ice as it sublimates in spring. These jets can reach heights of several hundred meters and create dark, fan-shaped deposits on the ice surface as they carry dust and sand particles along with the escaping gas. The study of Martian dust storms has revealed complex atmospheric dynamics that affect the entire planet. Local dust storms are common on Mars, but occasionally these storms grow to encompass the entire planet, as happened in 2018. These global dust storms can last for months and dramatically affect surface temperatures, atmospheric circulation, and the operation of solar-powered spacecraft. The 2018 global dust storms provided scientists with an unprecedented opportunity to study these phenomena using multiple spacecraft and rovers. Observations revealed that the storm began as a regional event, but quickly grew to cover the entire planet through complex feedback mechanisms involving dust heating, atmospheric circulation, and the release of more dust into the atmosphere. Martian weather patterns are driven by the planet's thin atmosphere, extreme temperature variations, and seasonal changes in atmospheric pressure. The lack of oceans means that Mars doesn't have the moderating influence of large water bodies that help stabilize Earth's climate. Instead, Martian weather is characterized by extreme temperature swings, powerful winds, and the transport of vast amounts of dust. The Curiosity rover has been monitoring Martian weather conditions in Gale Crater for over a decade, providing detailed measurements of temperature, pressure, humidity, and wind patterns. These observations have revealed daily and seasonal cycles that help scientists understand atmospheric processes and plan for future missions. Temperature variations on Mars can be extreme even within a single day. At the equator, temperatures might range from 20 degrees Celsius during the day to minus 80 degrees Celsius at night. These dramatic temperature swings are caused by the thin atmosphere's inability to retain heat, allowing surface temperatures to change rapidly as the sun rises and sets. The discovery of snow on Mars has added another dimension to our understanding of the planet's weather systems. The Phoenix lander directly observed snow falling from Martian clouds, though the snow sublimated before reaching the surface due to the dry atmospheric conditions. Orbital observations have also detected snow and frost formation in various regions of the planet. Martian clouds come in several varieties, including water ice clouds similar to those on Earth, and carbon dioxide clouds that form at much higher altitudes. The Mars Climate Sounder instrument on the Mars Reconnaissance Orbiter has mapped these cloud systems and revealed complex atmospheric circulation patterns that transport water vapor around the planet. The study of Martian atmospheric escape has provided crucial insights into how the planet lost its thick, early atmosphere. The MAVEN spacecraft has been monitoring this process since 2014, measuring the rate at which different atmospheric gases escape to space and identifying the mechanisms responsible for this loss. Solar wind interactions with Mars's thin atmosphere create complex plasma physics phenomena that accelerate atmospheric escape. Without a global magnetic field to deflect the solar wind, charged particles from the Sun can directly interact with the Martian atmosphere, stripping away atoms and molecules through various physical processes. MAVEN's observations have shown that atmospheric escape rates vary dramatically depending on solar activity. During periods of high solar activity, when the solar wind is more intense, atmospheric escape rates can increase by factors of 10 or more. This suggests that early Mars, when the Sun was more active, may have lost its atmosphere much more rapidly than previously thought. The isotopic composition of the Martian atmosphere provides additional evidence for massive atmospheric loss over geological time. The ratio of different isotopes of noble gases like argon and xenon in the current atmosphere suggests that Mars has lost the vast majority of its original atmosphere to space. Understanding atmospheric escape processes on Mars has implications for the habitability of exoplanets around other stars. Many potentially habitable exoplanets orbit red dwarf stars that are much more active than our Sun, potentially subjecting their atmospheres to even more intense stellar wind interactions than Mars experiences. The magnetic field remnants preserved in Mars's ancient crust tell the story of a planet that once had a global magnetic field similar to Earth's. These magnetic signatures, detected by the Mars Global Surveyor, are strongest in the southern highlands and suggest that Mars's magnetic field disappeared relatively early in the planet's history. The loss of Mars's magnetic field may have been caused by the cooling and solidification of the planet's core, which would have shut down the dynamo process that generates planetary magnetic fields. Alternatively, a massive impact might have disrupted the core's convection patterns, leading to the collapse of the magnetic field. Recent research has suggested that Mars might still have a partially molten core based on seismic observations from the InSight lander. If confirmed, this would raise new questions about why Mars lost its magnetic field and whether it might be possible for the planet to regenerate a magnetic field in the future. The InSight mission, which operated on Mars from 2018 to 2022, provided the first detailed measurements of Martian seismic activity. The lander's seismometer detected hundreds of Marsquakes, revealing that Mars is still geologically active despite its small size and age. These Marsquakes have provided unprecedented insights into Mars's internal structure, revealing details about the planet's crust, mantle, and core that were previously unknown. The seismic data suggests that Mars's crust is thicker than Earth's and that the planet's core is larger and less dense than previously thought. The detection of Marsquakes also has implications for the planet's potential habitability. Seismic activity can create fractures in rocks that allow water to circulate, potentially creating subsurface environments suitable for life. The energy released by Marsquakes might also drive chemical reactions that could support microbial ecosystems. The InSight mission's heat flow measurements revealed that Mars's interior is much cooler than Earth's, which helps explain why the planet became geologically inactive much earlier than our homeworld. The low heat flow also suggests that Mars's core solidified more quickly than Earth's, contributing to the early loss of its magnetic field and the subsequent atmospheric escape that transformed the planet's climate. The study of impact craters on Mars has provided a detailed chronology of the planet's geological history. Unlike Earth, where plate tectonics and erosion have erased most ancient craters, Mars preserves a nearly complete record of impact events spanning billions of years. This crater record allows scientists to determine the relative ages of different surface features and understand how the planet's geology has evolved over time. The Hellas Basin, one of the largest impact structures in the solar system, measures over 2,000 kilometers in diameter and reaches depths of up to 9 kilometers below the surrounding terrain. This massive crater, formed by an asteroid impact early in Mars's history, created a basin so large that it affects atmospheric circulation patterns and may have served as a reservoir for ancient lakes or seas. Crater counting techniques have revealed that different regions of Mars have vastly different ages. The heavily cratered southern highlands preserve surfaces that are over 4 billion years old, while the smooth northern plains show evidence of much more recent geological activity. This age difference supports theories about massive resurfacing events that may have shaped Mars's northern hemisphere. The study of Martian meteorite impacts has also provided insights into the planet's atmospheric history. When large asteroids strike Mars, they can blast rocks completely off the planet and into space. Some of these rocks eventually make their way to Earth as meteorites, carrying with them samples of the Martian atmosphere trapped in tiny glass bubbles formed during the impact. Analysis of these atmospheric samples has confirmed that the Martian atmosphere was once much thicker and had a different composition than today. The isotopic ratios of gases trapped in meteorites match those measured by spacecraft on Mars, providing independent confirmation of atmospheric escape processes and climate change on the red planet. The search for organic molecules on Mars has yielded increasingly promising results as analytical techniques have improved. The Curiosity rover has detected a variety of organic compounds in rocks from Gale Crater, including molecules that could be the building blocks of life or the remnants of ancient biological processes. These organic discoveries are particularly significant because they demonstrate that complex carbon chemistry can occur and be preserved on Mars despite the planet's harsh surface conditions. The presence of organic molecules doesn't prove that life existed on Mars, but it shows that the chemical ingredients for life were available and could potentially be preserved in the geological record. The seasonal variation in atmospheric methane detected by Curiosity adds another layer of intrigue to the organic chemistry story. The fact that methane concentrations change with the seasons suggests an active source that responds to temperature changes, possibly involving the release of trapped gases from subsurface reservoirs or even seasonal biological activity. The Perseverance rover's more advanced analytical capabilities have expanded our understanding of Martian organic chemistry. The rover's instruments can detect and analyze organic molecules with much greater sensitivity and specificity than previous missions, potentially identifying biosignatures that earlier missions might have missed. The concept of biosignatures, chemical or physical evidence of life, has become central to the search for life on Mars. These might include specific organic molecules that are produced primarily by biological processes, isotopic ratios that indicate biological activity, or mineral formations that require the presence of living organisms. However, distinguishing between biological and non-biological sources of organic molecules remains one of the greatest challenges in astrobiology. Many organic compounds can be produced by purely chemical processes, and the harsh Martian environment can alter or destroy organic molecules over geological timescales. The preservation potential for biosignatures on Mars depends heavily on local environmental conditions. Rocks that formed in neutral pH water environments and were quickly buried or protected from oxidation have the best chance of preserving organic molecules and other potential biosignatures over billions of years. Gale Crater, where Curiosity has been exploring, appears to have had ideal conditions for biosignature preservation. The crater once contained a lake with relatively neutral pH water, and the sediments that accumulated on the lake bottom were quickly buried and protected from the oxidizing surface environment. Jezero Crater, where Perseverance is currently exploring, was chosen specifically for its high potential for biosignature preservation. The ancient river delta in the crater represents an environment where organic molecules and potential microfossils could have been concentrated and preserved in fine-grained sediments. The search for microfossils on Mars faces unique challenges due to the planet's harsh surface environment and the small size of potential fossil remains. On Earth, microfossils are typically identified through their distinctive shapes and chemical compositions, but these features can be altered or destroyed by geological processes over billions of years. Advanced imaging techniques developed for Mars missions can detect microscopic structures in rocks that might represent fossilized microorganisms. However, distinguishing between biological and non-biological microscopic structures requires careful analysis and multiple lines of evidence. The study of extremophile organisms on Earth has expanded our understanding of where life might be able to survive on Mars. These remarkable organisms thrive in environments previously thought to be uninhabitable, including highly acidic hot springs, extremely salty lakes, and deep subsurface environments with no access to sunlight. Some extremophiles can survive in conditions that closely resemble those found on Mars, including low temperatures, high radiation levels, and extremely dry conditions. The discovery of these organisms has expanded the range of environments where scientists think life might be able to exist on the red planet. Perchlorate-reducing bacteria represent a particularly relevant example of extremophile organisms that might be able to survive on Mars. These bacteria can use perchlorate salts, which are abundant in Martian soil, as an energy source, potentially allowing them to thrive in the chemical environment found on the planet's surface. The study of analog environments on Earth, locations that share some characteristics with Mars, has provided valuable insights into potential Martian ecosystems. The Atacama Desert in Chile, Antarctica's dry valleys, and deep subsurface mines all serve as natural laboratories for studying how life might survive in Mars-like conditions. Research in these analog environments has revealed that life can persist in extremely harsh conditions by adopting various survival strategies, including forming protective biofilms, entering dormant states during unfavorable conditions, and utilizing alternative energy sources when traditional resources are unavailable. The concept of a deep biosphere on Mars has gained credibility as scientists have discovered extensive microbial ecosystems deep beneath Earth's surface. These subsurface communities derive energy from chemical reactions involving rocks and water, demonstrating that life can exist completely independently of surface conditions and solar energy. If a similar deep biosphere exists on Mars, it would be largely isolated from the harsh surface environment and could potentially have survived throughout the planet's climate transition from warm and wet to cold and dry. Such organisms might still be active today, representing a completely independent evolutionary lineage that developed separately from Earth life. The search for subsurface life on Mars will require drilling capabilities that go far beyond what current missions can achieve. Future missions may need to drill hundreds of meters or even kilometers beneath the surface to reach environments where life might still exist. The technical challenges of deep drilling on Mars are enormous, requiring sophisticated equipment that can operate autonomously in the harsh Martian environment. The drill systems must be able to penetrate various types of rock and soil while maintaining sterile conditions to avoid contaminating potential biological samples. Planetary protection protocols have become increasingly important as Mars missions have become more sophisticated and the possibility of finding life has increased. These protocols are designed to prevent Earth organisms from contaminating Mars and to protect any potential Martian life from being harmed by human activities. The forward contamination problem involves ensuring that spacecraft and instruments sent to Mars are thoroughly sterilized to prevent Earth microorganisms from being transported to the red planet. This is particularly challenging for missions that will drill into the subsurface or collect samples for return to Earth. Backward contamination concerns focus on protecting Earth's biosphere from potential Martian organisms that might be returned in samples. The Mars sample return mission will require unprecedented containment and analysis protocols to ensure that any returned samples can be studied safely without risk to Earth's environment. The ethical implications of discovering life on Mars extend far beyond scientific considerations. Finding even microbial life on another planet would fundamentally change humanity's understanding of our place in the universe and raise important questions about our responsibilities as we explore other worlds. If life is discovered on Mars, it would provide crucial insights into the universality of biological processes and the likelihood of life existing elsewhere in the universe. A second genesis of life in our own solar system would suggest that life might be common throughout the cosmos, dramatically increasing the probability that we are not alone. The study of Martian life, if it exists, could also provide insights into alternative biochemistries and evolutionary pathways that might be possible under different environmental conditions. Such discoveries could expand our understanding of the fundamental principles of biology and the range of conditions under which life can emerge and evolve. The implications of discovering life on Mars extend beyond biology into the realms of philosophy, religion, and human culture. Such a discovery would represent one of the most profound scientific breakthroughs in human history, comparable to the Copernican revolution that displaced Earth from the center of the universe. The knowledge that life exists beyond our planet would fundamentally alter humanity's cosmic perspective and our understanding of our place in the grand story of the universe. The technological innovations developed for Mars exploration have had far-reaching impacts on life here on Earth. Advanced materials designed to withstand the Martian environment have found applications in everything from medical devices to renewable energy systems. The miniaturization of scientific instruments for Mars missions has led to breakthroughs in portable analytical equipment used in environmental monitoring and medical diagnostics. Autonomous navigation systems developed for Mars rovers have contributed to advances in self-driving vehicles and robotic systems on Earth. The challenges of operating complex machinery on Mars with communication delays of up to 24 minutes have driven innovations in artificial intelligence and machine learning that benefit numerous terrestrial applications. The psychological and social aspects of Mars exploration have become increasingly important as we move closer to human missions to the Red Planet. The isolation, confinement, and extreme environment that future Mars explorers will face present unprecedented challenges for human psychology and group dynamics. Analog missions on Earth, such as those conducted in the Arctic, Antarctica, and isolated research stations, have provided valuable insights into how humans cope with Mars-like conditions. These studies have revealed the importance of crew selection, training, and support systems for maintaining mental health and mission effectiveness during long-duration space missions. The Mars Desert Research Station in Utah and the HIC's facility in Hawaii have served as testbeds for Mars mission protocols, allowing researchers to study how crews work together in isolated, confined environments while conducting scientific research and maintaining complex life support systems. The timeline for human missions to Mars continues to evolve as our understanding of the challenges and requirements becomes more sophisticated. Current estimates suggest that the first human missions to Mars could occur in the 2030s or 2040s, depending on technological developments and international cooperation. The journey to Mars will take 6 to 9 months each way, requiring life support systems that can operate reliably for over 2 years. The psychological challenges of such a long journey, combined with the knowledge that Earth is just a pale blue dot in the distance, will test human endurance in ways never before experienced. Landing humans safely on Mars presents engineering challenges that dwarf those faced by robotic missions. The spacecraft must be large enough to carry crew, life support systems, and equipment for surface operations, while still being able to land safely on a planet with a thin atmosphere that provides little aerodynamic braking. The entry, descent, and landing phase for human Mars missions will likely require new technologies such as supersonic retropropulsion, where rocket engines fire forward during descent to slow the spacecraft. This technique has been successfully demonstrated by SpaceX's Falcon 9 rocket landings, but has never been attempted on the scale required for Mars missions. Once on the surface, human explorers will face radiation levels much higher than those experienced on Earth or even on the International Space Station. Mars lacks a strong magnetic field and thick atmosphere to protect against cosmic radiation and solar particle events, requiring sophisticated shielding and monitoring systems to protect crew health. The development of in-situ resource utilization technologies will be crucial for sustainable human presence on Mars. The ability to extract water from the Martian soil, produce oxygen from the atmosphere, and manufacture building materials from local resources will reduce the mass and cost of supplies that must be transported from Earth. The MOXIE experiment on the Perseverance rover has already demonstrated that oxygen can be produced from the Martian atmosphere, converting carbon dioxide into breathable oxygen using a solid oxide electrolyzer. Scaling up this technology for human missions will require much larger and more efficient systems. Water extraction from Martian soil presents both opportunities and challenges. While subsurface ice is abundant in many regions, extracting and purifying this water for human consumption requires sophisticated processing systems that can operate reliably in the harsh Martian environment. The construction of habitats on Mars will likely involve a combination of pre-positioned equipment sent from Earth and structures built using local materials. 3D printing technologies using Martian regolith could enable the construction of radiation-shielded habitats before human crews arrive. The psychological benefits of having a permanent human presence on Mars extend beyond scientific research to include the inspiration and motivation that such achievements provide for humanity as a whole. The images and stories from human Mars explorers will capture the public imagination in ways that robotic missions, however successful, cannot match. The international cooperation required for human Mars missions could serve as a model for addressing global challenges on Earth. The scale and complexity of Mars exploration necessitate collaboration between nations, space agencies, and private companies in ways that transcend traditional political boundaries. The economic implications of Mars exploration are already becoming apparent as private companies invest billions of dollars in developing technologies for Mars missions. SpaceX, Blue Origin, and other companies are driving innovation in rocket technology, life support systems, and space manufacturing that will benefit both Mars exploration and Earth-based applications. The potential for Mars to serve as a backup location for human civilization has been proposed by various scientists and entrepreneurs, though this remains highly speculative and controversial. The challenges of establishing a self-sustaining human presence on Mars are enormous and would require technological capabilities far beyond what currently exists. The terraforming of Mars, the hypothetical process of transforming the planet's environment to make it more Earth-like, represents one of the most ambitious concepts in planetary science. Proposed methods include thickening the atmosphere, warming the planet, and introducing Earth organisms to create a biosphere. However, terraforming Mars would be an undertaking of unprecedented scale, requiring technologies and resources that may not be available for centuries or millennia. The ethical implications of such massive planetary engineering are also profound, particularly if indigenous Martian life is discovered. The study of Mars has revealed the importance of planetary magnetic fields in maintaining habitable conditions. Earth's magnetic field protects our atmosphere from solar wind erosion, and the loss of Mars's magnetic field likely contributed to its transformation from a potentially habitable world to the cold, dry planet we see today. Understanding how planetary magnetic fields form and evolve has implications for the habitability of exoplanets around other stars. Many potentially habitable exoplanets orbit red dwarf stars that are much more active than our Sun, potentially subjecting their atmospheres to intense stellar wind interactions that could strip away their atmospheres. The comparative planetology approach to studying Mars has provided insights into planetary formation and evolution throughout the solar system. By comparing Mars to Earth, Venus, and other planets, scientists can identify the factors that determine whether a planet becomes habitable and maintains those conditions over geological time. The role of planetary size in determining habitability has become clearer through Mars studies. Mars's smaller size meant that it cooled more quickly than Earth, leading to the earlier cessation of volcanic activity and the loss of its magnetic field. This size effect has implications for the habitability of smaller exoplanets. The discovery of seasonal methane variations on Mars has sparked intense debate about possible biological sources. While geological processes can also produce methane, the seasonal pattern suggests a source that responds to temperature changes which could be consistent with biological activity. The search for the source of Martian methane has become one of the highest priorities for future missions. Identifying whether the methane comes from geological processes, such as serpentinization reactions between water and rock, or from biological processes could provide crucial evidence about the possibility of life on Mars. The study of Martian atmospheric chemistry has revealed complex interactions between surface and atmospheric processes. The oxidizing nature of the Martian surface, caused by peroxide compounds in the soil, creates a challenging environment for organic molecule preservation, but also drives interesting atmospheric chemistry. The seasonal cycle of water vapor in the Martian atmosphere provides insights into the planet's hydrological cycle and the exchange of water between surface ice deposits and the atmosphere. Understanding these processes is crucial for planning future missions and assessing the availability of water resources. The discovery of opal deposits on Mars by the Spirit and Opportunity rovers provided evidence for relatively recent water activity on the planet. Opal forms from silica-rich water and can preserve biosignatures, making these deposits high-priority targets for future life detection missions. The study of Martian dust has revealed its global importance in planetary processes. Martian dust is extremely fine and can remain suspended in the atmosphere for months during global dust storms. This dust affects atmospheric heating, surface temperatures, and the operation of solar-powered spacecraft. The electrostatic properties of Martian dust create unique challenges for equipment design and human exploration. Dust particles can build up static charges that could damage sensitive electronics or pose health risks to astronauts. Understanding and mitigating these effects is crucial for future missions. The adhesive properties of Martian dust have proven to be both a blessing and a curse for surface missions. While dust accumulation on solar panels has ended several rover missions prematurely, dust devils and wind events have occasionally cleaned the panels, extending mission lifetimes far beyond their planned durations. The Opportunity rover operated for nearly 15 years, partly due to these fortuitous cleaning events. The chemical composition of Martian dust reveals a planet-wide mixing process that has homogenized surface materials over geological time. Unlike Earth, where different regions have distinct soil compositions, Martian dust shows remarkably similar chemistry regardless of where it's sampled, suggesting global transport by wind over millions of years. The study of Martian soil chemistry has revealed the presence of toxic perchlorates throughout the planet's surface. These oxidizing compounds pose challenges for both robotic missions and future human exploration, as they can damage equipment and are harmful to human health. However, some Earth organisms can actually use perchlorates as an energy source, raising intriguing possibilities for Martian life. The Phoenix lander's discovery of water ice just beneath the surface at high northern latitudes confirmed that Mars contains vast reservoirs of frozen water. The ice was so pure that it sublimated directly into water vapor when exposed to the Martian atmosphere, providing dramatic visual evidence of subsurface water resources. Ground-penetrating radar observations from orbit have revealed that subsurface ice extends to much lower latitudes than previously thought. These ice deposits represent a crucial resource for future human missions and could potentially harbor subsurface ecosystems protected from the harsh surface environment. The study of Martian permafrost has drawn comparisons to similar environments on Earth, particularly in the Arctic regions of Alaska, Canada, and Siberia. These terrestrial analogues help scientists understand how water ice behaves in Martian soil and what types of organisms might be able to survive in such environments. The discovery of recurring slope lineae initially generated excitement about possible flowing water on present-day Mars. These dark streaks appear seasonally on steep slopes and were thought to be caused by briny water flows. However, subsequent analysis suggests they may be caused by flowing sand, highlighting the challenges of interpreting remote observations. Despite this setback, other evidence for present-day water activity continues to accumulate. Radar observations have detected what appear to be subsurface liquid water reservoirs beneath the South Polar ice cap. though the interpretation of these signals remains controversial among scientists. The search for subsurface liquid water on Mars has been complicated by the planet's low atmospheric pressure and cold temperatures, which make liquid water unstable at most surface locations. However, briny solutions containing dissolved salts can remain liquid at much lower temperatures and pressures than pure water. Laboratory experiments have shown that perchlorate brines, which are likely to exist on Mars based on soil chemistry measurements, can remain liquid at temperatures as low as -70 degrees Celsius. These brines could potentially support microbial life and might be responsible for some of the seasonal changes observed on the Martian surface. The concept of habitable zones has evolved beyond simple temperature considerations to include factors like atmospheric pressure, radiation levels, and chemical environments. Mars today exists outside the traditional habitable zone for surface liquid water, but subsurface environments might still be habitable for certain types of organisms. The deep subsurface of Mars represents the most promising environment for present-day life. Several kilometers beneath the surface, temperatures would be warmer due to geothermal heating, pressure would be higher, and the environment would be protected from harmful radiation and the oxidizing surface chemistry. Drilling to these depths presents enormous technical challenges that are beyond the capabilities of current Mars missions. Future missions designed to search for deep subsurface life will require sophisticated drilling equipment that can operate autonomously and maintain sterile conditions to avoid contaminating potential biological samples. The study of impact-generated hydrothermal systems on Mars has revealed another potential habitat for life. Large asteroid impacts can create hot water systems that persist for thousands of years, providing energy sources and chemical environments that could support microbial ecosystems. The Curiosity rover's discovery of ancient mudstone deposits in Gale Crater provides evidence for long-lived aqueous environments that could have supported life. These fine-grained sedimentary rocks formed in calm water conditions and contain the types of chemical environments that are conducive to life as we know it. The preservation of organic molecules in these ancient mudstones demonstrates that biosignatures could potentially survive in the Martian geological record for billions of years. This discovery has important implications for the search for ancient life and the selection of landing sites for future missions. The Perseverance rover's exploration of Jezero Crater has revealed a complex history of water activity, including evidence for multiple episodes of lake formation and drying. The rover has collected samples from both igneous rocks that formed from ancient lava flows and sedimentary rocks that formed in aqueous environments. The diversity of rock types and environments sampled by Perseverance provides the best opportunity yet to search for signs of ancient life on Mars. The samples collected by the rover will eventually be returned to Earth for detailed analysis in terrestrial laboratories, with capabilities far beyond what can be achieved on Mars. The Mars Sample Return mission represents a crucial next step in Mars exploration, as it will allow scientists to apply the full range of analytical techniques available on Earth to Martian samples. These analyses could finally answer the question of whether life ever existed on Mars and provide insights into the planet's early environmental conditions. The technical challenges of the Mars Sample Return mission are unprecedented in robotic space exploration. The mission requires multiple spacecraft working in coordination across millions of kilometers of space, including a fetch rover, a Mars ascent vehicle, and an Earth return orbiter. The Mars ascent vehicle will become the first rocket ever launched from the surface of another planet, requiring technologies that can operate reliably after years of exposure to the Martian environment. The orbital rendezvous and sample capture must be executed with precision that makes docking at the International Space Station look simple by comparison. The timeline for Mars sample return has been extended due to budget constraints and technical challenges, but the mission remains a high priority for both NASA and the European Space Agency. Current plans call for the samples to arrive on Earth in the early to mid-2030s, potentially carrying the first definitive evidence of life beyond our planet. The study of Martian atmospheric dynamics has revealed complex circulation patterns driven by the planet's thin atmosphere, extreme temperature variations, and seasonal changes in atmospheric mass. Unlike Earth, where oceans moderate climate variations, Mars experiences dramatic seasonal changes as carbon dioxide freezes and sublimates at the polar caps. The Martian atmosphere undergoes a remarkable transformation each year, as roughly 25% of the atmospheric mass freezes out at the winter pole and then sublimates back into the atmosphere during spring and summer. This seasonal cycle creates global pressure variations and drives atmospheric circulation patterns unlike anything seen on Earth. Dust storms on Mars can grow from local events to planet-encompassing phenomena that affect global atmospheric circulation and surface temperatures. The 2018 global dust storms provided an unprecedented opportunity to study these processes using multiple spacecraft and surface assets. The role of topography in Martian atmospheric dynamics is particularly important due to the planet's extreme elevation differences. Olympus Mons rises 21 kilometers above the surrounding plains, while Hellas Basin extends 9 kilometers below the mean surface level, creating pressure variations that drive complex wind patterns. The study of Martian clouds has revealed water ice clouds, carbon dioxide clouds, and even clouds composed of dust particles. These different cloud types form at different altitudes and temperatures, providing insights into atmospheric composition and dynamics throughout the vertical column. The detection of aurora on Mars by the MAVEN spacecraft has revealed complex interactions between the solar wind and the planet's remnant magnetic fields. Unlike Earth's aurora, which are confined to polar regions by our global magnetic field, Martian auroras can occur anywhere on the planet where crustal magnetic fields interact with solar particles. The study of atmospheric escape processes on Mars has provided crucial insights into how planets lose their atmospheres over geological time. The MAVEN mission has measured escape rates for different atmospheric constituents and identified the physical processes responsible for atmospheric loss. Solar wind sputtering, photochemical escape, and impact erosion all contribute to atmospheric loss on Mars, with their relative importance varying depending on solar activity levels and atmospheric composition. Understanding these processes is crucial for assessing the habitability of exoplanets around other stars. The isotopic composition of the Martian atmosphere provides a record of atmospheric evolution over billions of years. The enrichment of heavy isotopes in the current atmosphere indicates that Mars has lost the vast majority of its original atmosphere to space, transforming from a potentially habitable world to the cold, dry planet we see today. The study of noble gas isotopes in the Martian atmosphere has provided particularly valuable insights into atmospheric evolution. These chemically inert gases serve as traces of atmospheric processes and have revealed details about the timing and mechanisms of atmospheric loss. The noble gas measurements from Martian meteorites and spacecraft observations have revealed that Mars lost its atmosphere through multiple processes operating over different timescales. Early catastrophic loss events, possibly triggered by massive impacts, may have removed significant portions of the atmosphere within the first billion years of the planet's history. The discovery of argon isotope ratios in the Martian atmosphere that differ significantly from solar values provides evidence for extensive atmospheric processing and loss. These measurements suggest that Mars has lost at least 90% of its original atmosphere, fundamentally altering the planet's climate and habitability potential. The study of seasonal atmospheric variations on Mars has revealed complex feedback mechanisms between surface ice, atmospheric composition, and global circulation patterns. As carbon dioxide sublimates from the polar caps during spring, it creates pressure waves that propagate around the planet and influence weather patterns in distant regions. The Mars Climate Sounder instrument on the Mars Reconnaissance Orbiter has provided detailed measurements of atmospheric temperature and composition throughout the Martian year. These observations have revealed the three-dimensional structure of atmospheric circulation and the role of dust in heating the atmosphere during global dust storms. The interaction between atmospheric dynamics and surface processes on Mars creates unique geological features not found on Earth. The formation of sand dunes, dust devil tracts, and wind-carved rock formations provides evidence for ongoing atmospheric activity that continues to shape the planet's surface. The study of Martian sand dunes has revealed active sediment transport processes that operate under the planet's current atmospheric conditions. Despite the thin atmosphere, winds on Mars can reach speeds sufficient to move sand particles and create migrating dune fields that change over timescales of years to decades. The Curiosity rover's observations of sand dune migration in Gale Crater have provided direct evidence for active aeolian processes on present-day Mars. Time-lapse images show individual sand grains moving across dune surfaces, demonstrating that Mars remains a geologically active world despite its apparent desolation. The formation of recurring slope lineae and other seasonal surface features may be related to atmospheric pressure changes that affect the stability of subsurface materials. As atmospheric pressure varies seasonally, it could trigger the release of trapped gases or the flow of granular materials down steep slopes. The study of Martian meteorology has revealed daily and seasonal patterns that help scientists understand atmospheric processes and plan future missions. Temperature, pressure, and wind measurements from surface missions provide ground truth for atmospheric models and help validate orbital observations. The Perseverance rover's weather monitoring equipment has detected dust devils passing directly over the spacecraft, providing detailed measurements of these atmospheric phenomena. These observations reveal the internal structure of dust devils and their role in lifting dust into the atmosphere. The search for seasonal biological activity on Mars has focused on detecting changes in atmospheric composition that might indicate metabolic processes. The seasonal variation in methane concentrations detected by Curiosity remains one of the most intriguing potential biosignatures, though alternative explanations involving geological processes cannot be ruled out. The development of life detection technologies for Mars missions has pushed the boundaries of analytical chemistry and miniaturization. Instruments capable of detecting organic molecules at parts per billion concentrations must be small enough to fit on spacecraft while robust enough to operate in the harsh Martian environment. The sample analysis at Mars Instrument Suite on Curiosity represents one of the most sophisticated analytical laboratories ever sent to another planet. This system can heat rock samples to over 1,000 degrees Celsius and analyze the released gases to identify organic molecules and determine their isotopic compositions. The scanning habitable environments with Raman and luminescence. For organics and chemicals instrument on Perseverance uses laser spectroscopy to identify minerals and organic compounds in rocks without requiring sample preparation. This non-destructive technique allows the rover to rapidly survey potential targets for detailed analysis. The development of drilling and sample handling systems for Mars missions has required innovations in robotics, materials science, and contamination control. These systems must operate reliably in extreme temperatures while maintaining the integrity of collected samples for analysis. The Perseverance rover's sample collection system represents a major advance in Mars exploration technology. The rover can drill cores from rocks, seal them in sterile containers, and cache them on the surface for eventual collection by the Mars Sample Return mission. The challenge of maintaining sample integrity during the multi-year journey from Mars to Earth requires sophisticated containment systems that can protect samples from contamination while preserving their scientific value. These systems must also ensure that any potential Martian organisms are contained to protect Earth's biosphere. The study of analog environments on Earth has provided crucial insights into potential Martian ecosystems and the types of biosignatures that might be preserved in the geological record. The Atacama Desert, Antarctica's dry valleys, and deep subsurface environments serve as natural laboratories for astrobiology research. Research in the Atacama Desert has revealed that life can persist in extremely arid conditions by utilizing trace amounts of atmospheric moisture and forming protective associations with mineral substrates. These findings have implications for the potential survival of life in the current Martian environment. Studies in Antarctica's dry valleys have shown that microbial communities can survive in permafrost for millions of years, remaining viable despite extreme cold and desiccation. These discoveries suggest that if life ever existed on Mars, it might still be preserved in subsurface ice deposits. The exploration of deep subsurface environments on Earth has revealed thriving microbial ecosystems that derive energy from chemical reactions involving rocks and water. These communities exist completely independently of surface conditions and solar energy, providing models for potential Martian life. The study of extremophile organisms has expanded our understanding of the limits of life and the range of conditions where organisms might survive on Mars. From bacteria that thrive in highly acidic environments to organisms that can withstand intense radiation, life on Earth has proven remarkably adaptable to hostile conditions. The discovery of organisms that can use perchlorate as an energy source has particular relevance for Mars, where these compounds are abundant in the soil. These bacteria demonstrate that the chemical environment on Mars might not be as hostile to life as previously thought. The development of planetary protection protocols has become increasingly important as Mars missions have become more sophisticated, and the possibility of finding life has increased. These protocols are designed to prevent contamination in both directions, protecting Mars from Earth organisms and protecting Earth from potential Martian life. The forward contamination problem involves ensuring that spacecraft sent to Mars are thoroughly sterilized to prevent Earth microorganisms from being transported to the red planet. This is particularly challenging for missions that will drill into the subsurface or search for signs of life. The backward contamination concerns focus on protecting Earth's biosphere from potential Martian organisms that might be returned in samples. The Mars sample return mission will require unprecedented containment and analysis protocols to ensure that returned samples can be studied safely. The ethical implications of Mars exploration extend beyond planetary protection to include questions about human rights to explore and potentially colonize other worlds. The discovery of life on Mars would add new dimensions to these ethical considerations and might affect how humanity approaches the exploration and development of the red planet. The potential for Mars to serve as a second home for humanity has captured the imagination of scientists, engineers, and the general public. However, the challenges of establishing a self-sustaining human presence on Mars are enormous and would require technological capabilities far beyond what currently exists. The psychological and social challenges of long-duration Mars missions have become increasingly important considerations as we move closer to human exploration of the red planet. The isolation, confinement, and extreme environment will test human endurance in ways never before experienced. The development of closed-loop life support systems for Mars missions requires technologies that can recycle air, water, and waste with near-perfect efficiency. These systems must operate reliably for years without resupply from Earth, making them far more sophisticated than anything currently used on the International Space Station. The production of food on Mars will likely require advanced agricultural techniques adapted to the planet's low gravity, limited atmosphere, and soil chemistry. Hydroponic and aeroponic systems may be necessary to grow crops in controlled environments protected from the harsh Martian surface conditions. The construction of habitats on Mars will need to address multiple challenges including radiation protection, atmospheric pressure containment, and thermal regulation. These structures may need to be partially buried or constructed using local materials to provide adequate protection for human occupants. The development of transportation systems for Mars exploration includes not only the spacecraft needed to travel between Earth and Mars, but also vehicles for surface exploration and eventual return journeys. These systems must be reliable, efficient, and capable of operating in the challenging Martian environment. The economic implications of Mars exploration are already becoming apparent as private companies invest billions of dollars in developing technologies for Mars missions. These investments are driving innovation in rocket technology, life support systems, and space manufacturing. that will benefit both Mars exploration and Earth-based applications. If you've made it this far through our Martian journey, please hit subscribe and give this video a thumbs up, and check out the video on your screen. How small are we inside the Milky Way, where we explore our place among billions of stars and the mind-blowing distances that make Mars seem like our next-door neighbor? See you there!